In September 2020, 6 months after it was originally scheduled, the five of us set off on a beam time to the ELETTRA Synchrotron in Basovizza in Italy. The aim of the experiment was to study the reaction between a molecule called 6,13-pentacene quinone and hydrogen atoms. In particular, we wanted to understand if the oxygen atoms react with the hydrogen atoms and leave as water molecules. To do this, we used an experimental technique called X-ray photoelectron spectroscopy, or XPS for short.
To do our experiment, we need a source of X-rays. It needs to be very intense and bright, but also tunable. We need to be able to change the energy of the X-rays we are using very quickly. And so we use a synchrotron. What is a synchrotron? A synchrotron is a storage ring for charged particles, in our case electrons, that forces those particles to travel around in a closed loop. High energy electrons travelling close to the speed of light are injected into a vacuum chamber in the shape of a ring, and a system of magnets and electric fields are used to push these electrons and accelerate them around the ring. A radio frequency cavity pushes or kickstarts the electrons at a set point on their path around the ring, and this bunches the electrons together or syncs their path around the storage ring. And so we have a synchrotron with packets of electrons travelling in an almost circular path at close to the speed of light. Every time the direction of the electron is changed by a magnetic field to force them back into the circular path, the electrons lose energy and slow down. This lost energy is emitted as very intense X-rays that travel in a straight path to create a beamline. By making a hole in our storage ring, we can let this beam of light travel out of our synchrotron and direct it towards the experiment. This light is extremely bright, 1,000,000 times brighter than the light that comes from the sun to the Earth, and contains wavelengths all the way from the infrared to hard X-rays like those used for medical exams. And so we have our source of X-rays with high intensity and variable wavelength travelling in a straight line that we can shine directly onto our sample.
The actual synchrotron is located in the hills outside of Trieste by the town of Basovizza, a real estate agent's stone throw from the Slovenian border. It's placed close to Trieste, both to connect the area to the rest of Italy and heal past atrocities, as well as to acknowledge its history as a city of science.
Travelling to Trieste normally entails a 2-flight hop via Amsterdam or Frankfurt. However, given the COVID-19 situation, we decided to drive our team of 5 and the necessary equipment the 1,500 kilometers or so from Aarhus to the small village of Basovizza, where the ELETTRA Synchrotron is situated.
So we had to bring a lot of equipment from the lab so that everything was ready and set to go, both to ensure compatibility between certain parts, but also to allow us to perform the actual experiments. And we brought an atomic oxygen doser, a self-modified atomic hydrogen doser. We brought 2 molecular dosers to go with all of this. We had compatible power supplies and temperature readers. We even went as far as to bring our own specific tools and components, such as spiral connectors, extra wire, screwdrivers and tweezers.
Our equipment packed and the van loaded, we embarked on the journey, reaching the German border before crossing the busy port of Hamburg by lunchtime. Picking up speed on the Autobahn, we pushed on, taking a break close to Göttingen before reaching the goal of day 1, a hotel close to Nuremberg. We were sure to visit a scale replica of the Saturn V rocket. The next morning we headed on past Munich and towards the Austrian border, where we took a final break before embarking on the most scenic part of the journey through the Alps. After recharging over coffee in the Italian Alps, it was down to Klaus to deliver us the final 100 kilometers or so to Basovizza.
So all components came in pairs for redundancy, such that a single component failure would not be a huge problem. This of course meant that we had to transport, unpack and eventually repack all of these fragile components. But the most nerve-wracking part of this was the on-location reassembly of different components before installation on the chamber. There are many unpredicted setbacks during such a trip. For instance, we have to file down some of their equipment to install ours. Luckily everything went smoothly, and after that we could get the system up and running. What a relief when everything works.
We prepared a thin film of the molecules on a surface and then exposed it to X-rays of a particular energy produced by the synchrotron. The incident X-rays cause electrons to be emitted from the innermost levels of the different atoms in the molecule. Let us consider electrons from the oxygen atoms only. The electrons from the oxygen atoms will have an energy x. If the incoming hydrogen atom attaches to the oxygen atoms, we expect the energy of the electron to be different. Let's say y. This change in the electron energy then gives us an idea of the chemical reaction between pentacene quinone and the hydrogen atoms. Getting the data is only half the job done. Now it's time to sit and look through thousands of spectra to find the needle in the haystack.